Okay, finally we're going to want to be able to discuss numerical information about a chemical reaction. And this field of study is known as stoichiometry, numerical relationships between reactants and reactants and other reactants, or even products and products. Okay, so we can answer questions. So how much product can I make if I have so much reactant, X amount of reactant? If I have 10 grams of butane, how many moles of carbon dioxide am I going to produce? Or if I say I want to make Y amount of product, okay, I want to make 20 grams of silver chloride. How much silver nitrate do I need? How much reactant do I need? Or let's say I have Z amount of B, a reactant. So say I have 10 grams of carbon in our first example. How much cobalt-2 oxide do I need to react it with it completely? Okay, all of these questions can be answered utilizing stoichiometry. Okay, a good analogy for the stoichiometry would be thinking about ingredients to make something at home in the kitchen, food. Here's a very simple example from your textbook. Here's a really simple recipe for a pizza. So I've got 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese. I throw those together, throw it in the oven. I'm going to produce 1 pizza. Okay? So you can ask simple questions. Well, how many pizzas can I make if I have 6 cups of cheese? Okay? Well, there's a relationship in this ingredients list. If I have 2 cups of cheese, I have 1 pizza. So that can give us an equality. 2 cups of cheese equals 1 pizza. Okay? So if I want to, I can create a conversion factor from those. I can say that if I have 2 cups of cheese, I can make 1 pizza. Or if I made 1 pizza, that means I had to have 2 cups of cheese. So to my original question, if I have 6 cups of cheese, you could have easily probably calculated that we're going to get 3 pizzas out of that. But you did this math in your head. You used a conversion factor saying that if I have 1 pizza, I know I need 2 cups of cheese. And so cups are going to cancel out, giving us pizzas. And that will give us 3 pizzas. So this very simple analogy is going to hold true for any chemical reactions. You can think about this ingredient list and this recipe as a reaction. You have a relationship between all of your ingredients and your product, what you're making. Okay? So as simple as this seems, that is how simple all of our stoichiometric calculations are going to be. So let's do an actual one. Let's say we have this ingredient list. Okay? If we have so much glucose, 1 mole of glucose and 6 moles of oxygen, we can produce 6 moles of carbon dioxide and 6 moles of water. Okay? So if we're given the fact that we have 0.1 moles of glucose, we can ask questions like how many moles of water are made. Okay? And again, just going back to our relationship between our coefficients, 1 mole of glucose is going to make 6 moles of water. So we can have conversion factors for that. So if I have 1 mole of glucose, I will make 6 moles of water. And of course, with every conversion factor, we can make 2. We can flip these to suit our needs. Okay, so I've got 0.10 moles of glucose. Okay, and I want to know how many moles of water I'm going to make or produce. Okay, well, we know that we want to convert moles of glucose to moles of water, so I'm going to cancel out moles of glucose. So if I have 1 mole of glucose, I know I'm going to make 6 moles of water. Moles of glucose will cancel out, and so we get 0.60 moles of water. Additionally, we can start out with a mass of a reactant and figure out how much mass of a product we're going to need. And this is actually going to be much more useful because we know in the laboratory we don't have individual instruments that tells us how many moles we have of a substance. Well, we do have scales that can tell us how many grams or milligrams of a substance we have. So of course we can go from any reactant to moles of a reactant. We can convert mass to moles using, of course, the molecular weight as a conversion factor. We can convert moles of anything to moles of anything if we have our balanced chemical equation. All we're going to need here is our coefficients from our balanced chemical equation. And then we can go moles to grams again using molecular weight or molar mass. So in this instance, we can go from grams of A to moles of A. 1 mole of A, how many grams of A that is, depending on the substance. Depending on the coefficients, there's moles of B will be produced from how many moles of A. And then one more additional conversion factor. If we have 1 mole of B, how many grams of B do we have? And of course, grams is going to cancel out. Moles of A will cancel out. Moles of B will cancel out, giving us final answer units of grams of B. Okay, so let's do an example of that. Okay, let's say we have 452.5 grams of octane. How many grams of carbon dioxide will we produce? Okay? Well, let's think of a game plan. Okay, we're going to go from grams of octane, C8H18, to moles of octane. And then since we're after carbon dioxide, we're going to convert that to moles of CO2 using our balanced chemical equation. So we look here and we can see that 16 moles of carbon dioxide are produced from 2 moles of octane. And then finally we can go to grams of CO2. Okay, of course we're going to need molar masses here and here, so that's one thing you should of course go do. Calculate the molar mass of octane and molar mass of carbon dioxide. I won't go through that math, but again, you can 8 carbons times the molar mass of carbon plus 18 hydrogens times the molar mass of hydrogen will give you the molar mass of octane. Okay, so we're starting out with 452.5 grams of octane, C8H18. If you calculated the molar mass of octane correctly, you should have gotten in 1 mole of C8H18, I got 114.23 grams. And then, just as we said, for every 16 moles of carbon dioxide produced, I need 2 moles of octane. So in 2 moles of octane, CH18, they will produce 16 moles of CO2. And then finally, so I'm here in my calculations, I want to get to here, and just one more calculation in 1 mole of CO2. I calculated a molar mass of 44.01 grams of CO2. Moles of carbon dioxide cancel out. Moles of octane cancel out. Grams of octane cancel out, leaving me grams of CO2. And if we throw that in our calculator, we're going to get a value of 1395. Okay, additionally, if we go back to sort of our pizza analogy, we asked the question, how many pizzas can I make if I have 6 cups of cheese? A big assumption there was that we have enough of the rest of the ingredients so that we can make our 3 pizzas. That certainly won't always be the case. So if we have a scenario where we have 4 crusts, 15 ounces of tomato sauce, and 10 cups of cheese, how many pizzas can we make? Well, if we calculate how many pizzas we can make from each of the ingredients, 4 crusts will give us 4 pizzas. 15 ounces of sauce will give us 3 pizzas. And 10 cups of cheese will give us 5 pizzas. Each of the ingredients indicates that we can make a different amount. So how many can we really make? Okay, of course, we can only make 3 pizzas, because after we run out of sauce, we no longer have enough ingredients to make pizzas per our recipe. So once we run out of sauce, we can't make any more pizzas. So the highest number of pizzas we can make are 3. There's no way we can make 4 pizzas because we ran out of sauce. And there's certainly no way we can make 5 pizzas. Okay? So in that sense, the number of our sauce limits how many pizzas we can make. It gives us the least amount of product, least amount of pizzas, and so that tells us how many pizzas we can make. And that same thing is true for chemical reactions. One of our reactants, if there's more than one, will limit how much product we can make. We refer to that as the limiting reactant or limiting reagent. Okay, once we make however much product our limiting reactant gives us, we're going to run out and our reaction will stop. Everything else that's not completely consumed we call excess reactants, just like in pizzas. We have leftovers, cups of cheese, leftover crust. Put that back in our pantry. We've got excess. Okay.